we will talk about more general factor. So let's define this concept, which is, very natural generalization of the K factor we discussed before. Let's say you have a given graph G and a function f from Bg to natural number. This is the set 0, 1, 2, 3, natural number or 0. We say an f factor of G is a spanning subgraph H such that degree of a vertex in H is same as the value of the f at V. So if you take a constant function f, then it's same as K factor. But this is obviously more general concept than K factor and also a very natural generalization of K factor. And we want to ask the question, when can we find the specific f factor in graph G? So there is certain function f that's what we desired. And when can we find it? In fact, there are ways to reduce the problem of finding f factor into the problem of finding one factor. And how do we do that? So we want to reduce this reduction of f factor to one factor. So assume we have a graph G. And also f, a function. And assume that, of course, f of, say, w is at most the degree of w for all vertices in G. If this is not satisfied for one single vertex, then it's obvious that f factor does not exist in G. This is obvious necessary condition. Then what do? We construct H. Let's say we have a G here. Then our f is, say, 2, 1, 2, 1. Give me a moment. Let's keep a bit more. Yeah, let's say 1. This is our G. And then how do we construct our H? We do it this way. So let E of W as the degree in G minus F of W be the excess degree. Then excess degree is what? Here 1, here 3, here 1, here 1, here 1, right? So its degree is 4, and then you subtract 1, which is 3. Degree is 2, you subtract 1, which is 1. 1, 1, 1. And then what do we do is that the following. For each vertex B in G, we replace this with a copy of complete bipartite graph. So I don't remember whether we defined this case of AB, which is complete bipartite graph with A vertices and B vertices with all edges between. So, complete bipartite graph with degree, comma, axis, having parts A of B and B of B of size degree and excess degree respectively. So what do we have here? So you have a degree many vertices, degree many vertex, degree many vertex, degree many vertex, degree many vertex, and excess degree many, excess degree many, excess degree many vertex, excess degree many, excess degree many vertex, and then we make it complete. And what do we do? And for each H UW in G, we add an H joining one vertex of AB to one vertex of AW in such a way that each vertex of AB participates in exactly one such edge, meaning that you add this edge. So for this edge, you add this. For this, you add, okay, let's do this way. For this, you add this. For this, you add this. And for this, you add this. For this, you choose one of these, which is not used, which is this. You choose one of these, which is not used, let's say this. And for this set, you choose one that's not used, choose one that's not used, you add this. You choose one that's not used, you choose one that's not used, you add this. So you get this graph H. Then it's not easy to actually check that the following theorem holds. If you have a multigraph, so this F vector is defined on, can be also defined on multigraph, right? So you are allowed to take more than one multiple edges, which actually increase the degree. So unlike the perfect matching case, the multigraph actually makes a difference in case of vector. So you consider this multigraph. So multigraph G as an F vector if and only if the graph H constructed from G as above has one vector. Finding one vector in H is same as finding F vector in G. You can kind of see, right? Already, if you have, say, F vector, give me a moment. Let's say you have a one vector. Yeah. Actually, I have not drawn it in a careful way. There are no F vector here, so let's change this to 2. Let's say. Sorry, let's change this to 1. Then xs is 2. Yeah. So what do you have? So if you have say 1 factor here, then what? Taking these out, and then you just consider, this edge, this edge, this edge, and put them together. Then what degree you get here? That's exactly the difference between these two. Degree minus xs, which is f value. So you can already see the connection between these two. On the other hand, if you have f factor here, then you have a natural choice of edges, and then all the remaining things are complete bipartite graph, which are balanced. Complete bipartite graph where both parts have size 3 and 3, 1 and 1, 1 and 1, 2 and 2, 1 and 1. That has a perfect match. So that gives you 1 factor. So, proof is what I just explained. Assume we have a f factor in G, and these edges leave EOB vertices of AV unmatched. And these match into BV, forming the 1 factor in H. On the other hand, assume we have a 1 factor in H. Then, from this 1 factor, we delete the vertices in BV and also the vertices in AV, which was matched into this BV, and it leaves FOB vertices of degree 1 corresponding to B. And we do this for all V. And we merge the remaining FOB vertices of each set AV. This yields a subgraph of G with degree FOB at each vertex V. So this gives you the difference. Then what? This construction and this theorem, allows us to use any, say, algorithm to find the 1 factors that can be used. Those algorithms can be used to test find the f factors in general graph. So essentially using this trick, any theorems about f vector can be reduced into the theorems about one vector. It's a matter of how complicated it gets when you try to transform one to other. Then using this idea and maybe a bit more idea to make it actually work, we can prove the following theorem, which is called the Tutte theorem, Tutte's F vector theorem. Which is about existence of F vectors. So for that, let's define some terminology. Say for function f defined on the vertices, we let that the f of s as a vertex set as a summation of this f on all the vertices. And then also let q of s and t for two vertices s and t, we denote this with the number of components C of G minus S union T, which satisfy the following, such that the number of edges between C and T plus F of BC is odd. So maybe so you have S and T, and then you have certain C. You count the number of edges between C and F, and you count the F value. F value 2, 3, 1, you add them, you sum them, and then altogether it's odd, then you count such number of components. That's how this QST is defined. And the following theorem holds. Thus, F vector theorem says that the graph G has an F vector if and only if QST minus you consider all the vertices in T and then consider its degree in the graph G minus S, and then you subtract. And then that's at most Fs minus Ft. I mean, this holds for all S and T. Then, it has an F vector. So, yeah, we will not prove this theorem, but basically its proof uses above construction and then do some like technical analysis, then you can see. For one, if you just take F to be 1 for all V and say T equal empty set, then this condition is actually equivalent with the Tutte's one factor theorem. So, as we will not prove this theorem, maybe we see one application of this theorem. So let's say you want to find, again, perfect matching, one factor. Then for simple graph, let's say three regular graphs. There are three regular graphs without one factor. For example, the smallest such graph, if you want to find one, we can consider this graph. So you take a complete graph on 5 vertices, and then you give me a moment. Yep. You delete these 3 edges. Path of 3 vertices, and then 1 edge. Path of 3 vertices and 1 edge. Path of length 2 and then 1 edge. Then this does not have a perfect matching. So 3 regular graphs might not have one factor. But here, this has very weak connectivity. There are cut edges, right? Then one might ask that whether, I mean, if you have a 3 regular graph with who's like more connected, so it doesn't have cut edge, then does it have always have one factor? It was actually proved by Peterson in 1891 that every 3 regular graphs without cut edge has one factor. And it was proved without using Tutte theorem, but using this Tutte one-factor theorem, one can easily deduce this from the, Tutte one-factor theorem. How do you show it? In order to use the Tutte one-factor theorem, we need to check that the Tutte condition holds for such a graph. So let's say, let X be a set with maximum deficiency. And C be an odd component of G minus S. You have S, and then you have C. Then what do we know? You have a condition of being 3 regular. So we have 2 conditions, 3 regular and then no cut edge. Then what do we know is that what do we get the information is that we get the information about the edges between these 2 and or these 2 and these 2. So between component and S. That will give us the information about the number of odd components here. How? As G is 3 regular. What do we know? If you take all the vertices in C, then add its degree, and that's 3 times C. Easy. And 3 times C is an odd number. But this is also same as the what? Number of, so if you have a graph here, then what? 3 plus 3 plus 3 is what? You count this 1, 2, 3, 1, 2, 3, 1, 2, 3. Then all the edges here are counted twice, and all the edges between here are counted once. So this is actually same as the number of edges between S and C plus twice the number of edges within C. And that's odd. And this is even number. So what do you know? Hence, the number of edges between S and C is odd. But what do you know? But she has no cut edge. So that means this doesn't happen. This one edge doesn't happen. It cannot happen there because if there are only one edge here, then this is a cut edge. So it is at least 3. One edge cannot happen, two edge cannot happen because this is even, so at least three. And what do we know? If we count the number of edges between S and the remaining part, what? You have S and the remaining, you count the number of edges. Because this is three regular, all the vertices here sends at most three edges to here. So this is at most 3 times S. It might send some edges inside S, so it could be lower, but it's at most 3 times S. But also what we shown is that every odd component sends at least 3 edges here. At least 3 edges, so we have this. This shows that the number of odd component in G minus S is at most S. This provides a touch condition. Hence, G has a one factor. So this proves what we want. Okay, so today we learned about Tutte's theorem and Tupper's formula, which gives the, size of the largest matching in G. And also we learned about Tutte's F factor theorem, which give us about the criteria to check for the existence of F factor. And yeah, that's what we learned. And next time we will talk about some algorithmic aspects of the matching. If you want to find the maximum matching, how can you find? So that's what we will discuss next time. Thank you for listening. See you next time.